Hello, welcome to the third week. In this week, we'll be discussing some most fascinating and intriguing topics in theoretical computer science. Up to this point, we have learned how to compute the time complexity of an algorithm, such that we're able to tell and compare algorithms' efficiency. We also have established that some problems are easy and some are difficult. This week, we will discuss the complexity of problems and characterize how hard a problem is. We will talk about the different classes of problems. Okay, let's get started. How to characterize how hard a problem is? Its difficulty is reflected by how easily we can solve it. Problem A is easy because its algorithm, and to be more specific, its best algorithm is very efficient. Problem B is hard because its best algorithm is very complex. So yes, we can characterize how hard a problem is based on the efficiency of its best algorithm. Ever since computers became widely available, people all around the world have created algorithms to solve computational problems. Especially given the current hype on AI, it almost creates this illusion that computers are invincible and can be used to solve any problems. So around the 60s and 70s, it was recognized that the problems computer scientists were working on seemed to fall into two loose categories. Ones that were easy to solve with fast algorithms, and ones for which it seemed to be impossible to find any efficient algorithm at all. Theoretical computer scientists started to find a practical way to distinguish between easy and hard problems. What defines an efficient algorithm? Most of the algorithms we have seen so far have been polynomial time algorithms, including the big O of n, n squared, n cubed, log n, which we know are fast algorithms, especially comparing to, say, exponential algorithms, such as 2 to the power of n. In computer science, easy problems are the ones that can be solved in polynomial time. It means that their complexity is in big O of n to the power of k, where k is a constant. Not all problems can be solved in polynomial time. So say a problem is hard when we could not find a polynomial time algorithm to solve it. We're either not smart enough to find a fast algorithm, or such an algorithm doesn't exist. Here is an example of one of these hard problems. Determine if an undirected graph has a Hamiltonian cycle. A Hamiltonian cycle of an undirected graph is a simple cycle that contains each and every vertex of the graph. A cycle is a path of existing edges in the graph that circles back to the starting point. A simple cycle means that each vertex can only be visited once on this cycle. Example graph A has an Hamiltonian cycle, but graph B does not. We can use a brute force algorithm to solve this problem, meaning given the graph G, we can exhaustively enumerate all possible permutations of all the vertices and check if it represents a Hamiltonian cycle. So for this example graph here, we can write all possible permutations of vertices like this. So how many possible permutations in total? So let's say we have n vertices in this graph. So in each permutation, the first position, we have n possible choices. And the second position, we have n minus 1 possible choices. The third position, we have n minus 2 possible choices, and so on and so forth. So what's this? That's the factorial of n. We could have a better algorithm than the brute force algorithm to solve this problem. However, no one has ever found a polynomial time to solve this problem. And for a small graph like this one, it won't be difficult for us to tell that a Hamiltonian cycle does not exist. You may wonder, perhaps we're just not smart enough to find a polynomial time algorithm to solve a hard problem. And what should we do if we do not even know the algorithm to solve a hard problem at all? And why is this relevant and important? We're going to spend a few more slides on the first question next. And here we have a brief answer to the second question. To become a good algorithm designer, you must understand this line of research. If you can establish a problem as hard, you provide good evidence for its intractability. You would then do better to spend your time developing a approximation algorithm or solving a tractable special case, rather than searching for a fast algorithm that solves the problem exactly, which may not even exist. To show a problem is hard, we're not trying to prove the existence of an efficient algorithm, but instead to show that no efficient algorithm is likely to exist. There are three key concepts before we reveal the theoretical work. First, we formalize the problems as decision problems. That is, the answer can only be yes or no. Then we show a technique reduction that transforms different problems in polynomial time, such that we'll be able to show which problem is harder than another one. Last, we show an example hard problem and show how other hard problems can be compared with it. There are various ways of how problems can be answered. Could be an integer, a boolean, a float, a word, or even a picture. In order to enable comparing different problems, we formalize a problem as a decision problem. There are two conditions to satisfy. First, the answer to any input instance is either yes or no. Second, the decision is deterministic. For example, let X be, does the set S contain the value 3? And the input instance should be a well-defined set, such as 1, 5, 3, 8, 7. This is a decision problem. The second example is the famous Turing's halting problem. This is a decision problem, even though we know there is no algorithm that can solve it for all possible programs and inputs. This shows some decision problems are easy and some can be very hard. The third example is not a decision problem. An input instance is the toss of a coin. Although the answer is either yes or no, the answer is not determined by the detail of the instance, since tossing the coin is a random event and its outcome cannot be determined. You may wonder, many problems we see are not decision problems and are optimization problems, for instance, where its answer is often the best or the optimal value. By considering only decision problems, are we ignoring the vast majority of optimization problems? Well, not necessarily. We can impose a bound on the value to be optimized in order to convert an optimization problem into a related decision problem. We also know that the decision version of the optimization problem is not harder than the original problem, since we can solve the decision problem by solving the optimization problem. In this example, we show the shortest path problem and its corresponding decision problem. Now we're ready to talk about the definition of class P, which is the set of all decision problems that can be solved using a computer in polynomial time. Most of the problems we have seen so far, such as searching and sorting, fall into this P class. The class NP has a bit more complex definition. First, we distinguish between solving a problem, that is, actually finding the answer, and verifying a solution, that is, checking the details to make sure they are correct. The class NP is the set of all decision problems that can be verified in polynomial time. Let's not be concerned about how a solution is found and imagine it is guessed by a magic computer, non-deterministic Turing machine. All we need to do is to verify if a guessed solution is correct in polynomial time. We know the Hamiltonian cycle problem does not have any polynomial time algorithm yet, so it may not be in class P. What about class NP? When we are given a sequence of vertices, can we verify if this is a correct answer in polynomial time? Yes, we only need to go through all the vertices in this sequence once and see if there are edges connecting all adjacent pairs of vertices. So this problem can be verified in polynomial time. It is in class NP. Now let's see the relation between P and NP. It's first important to see that P is contained in NP. If we have an algorithm that correctly solves a problem and provides details of the solution, then we could use the same algorithm to verify the correctness of the yes-no solution, guessed by the magic non-deterministic Turing machine. So all problems that can be solved in polynomial time can also be verified in polynomial time. Second, most of these really hard problems that nobody could find good algorithms for actually do have the property that a yes answer can be verified quite easily. Here is the most intriguing question in theoretical computer science. Is P equal to NP? Are there any problems in NP that are not in P? Is there any problem that can be verified in polynomial time but not solved in polynomial time? It would seem that there absolutely must be such problems. If not, then the two classes P and NP are equal, which virtually nobody believes. To answer this question, people started trying to find the most difficult problems in NP. By the same token, if we can prove that the most difficult problems in NP are also in P, then we can prove P equals NP. How can we identify the hardest problem in NP? Since we quantify how hard a problem is by looking at the efficiency of its best algorithm, how can we do this if we do not even know the best algorithm to solve a problem? Turns out there is a clever way to go around this, when what we are concerned with is only to compare how hard two problems are. How to show, for instance, problem A is not harder than B. We do this indirectly by showing that if we could find an efficient algorithm for B, this would immediately give us an efficient algorithm for A. If we can solve problem A by solving problem B, we say A is not harder than B. This process is called reduction. We use a polynomial time reduction algorithm to solve a decision problem A in polynomial time. Given a polynomial time decision algorithm for another problem B, we demonstrate that any instance of A can be transformed in polynomial time into an instance of B in an answer-preserving way. Answer-preserving means that if the answer to A on that specific input is yes, then the answer to B on the transformed input should also be yes, and vice versa. We say A reduces to B if we can use a polynomial time reduction algorithm that converts instance alpha of A into instance beta of B. If there is an efficient polynomial time algorithm for B, we instantly get an efficient polynomial time algorithm for A, since a polynomial plus a polynomial is still a polynomial. Here is an example. Although both problems are extremely simple, let's focus on the relationship between them rather than their exact solutions. We need to find algorithm for A. We try to reduce A to problem B. Let's say we have an algorithm for problem B. And what we need to do is, given an input A, so that will be a set S, can we convert it into an input instance to algorithm B? So that would be T and K. T is a set and K is a value. So how can we convert S to TK such that when we give that specific input instance to algorithm B, if it gives us an answer yes, then we would also have an answer yes for the problem A. If it gives us an answer no, then we would also have an answer no to the original problem A. So how can we do the transformation here? We can simply let T be S and K be 4. So if we give S and 4 to algorithm B, and algorithm B will tell us, does S contain 4? If the answer is yes, then we also have the yes answer to problem A, and vice versa. For this example, we can actually go both directions. Can we reduce problem B to problem A? So let's draw the same diagram. We need to figure out an algorithm for B where we can use an algorithm for A when we have an input B, so that would be T a set, K a value. How can we convert that into an input to A? So that would be a set S. So when algorithm A tells us yes, we have a yes answer to the original problem B. If the algorithm tells us no, we have a no answer to problem B. So how do we do the transformation? So algorithm A tells us whether or not a set S contains the value 4. Question B needs us to tell whether or not a set T contains a more general value K. So we have to tie together the specific value 4 and a more general value K. There are actually different ways to do the transformation. One example would be we can let all the numbers in S be 4 times T, all the numbers in T minus K plus 1. So if we give the set S to A, and algorithm A will tell us whether or not we have a number that is 4. So if a number is 4 in S, it means that we have a number in T with a value K. That's the only case when T minus K plus 1 times 4 equals 4. So by now, it won't be difficult for you to figure out there are other ways to do the transformation. For instance, we could set all the numbers in S as the numbers in T minus K plus 4. Here is another example reduction. Solving A requires counting, but solving B involves adding. So how can we transform an instance of A into an instance of B? The key insight is that counting is equivalent to adding ones. So we can transform the instance of A into an instance of B by replacing every positive integer by 1 and every negative integer by minus 1. So for instance, we have a set S as an input instance for problem A. So we have a set of integers. And then we can create a set of T Correspondingly, by converting all the positive integers as ones and all the negative integers as minus ones. So when there are more positive than negative integers in set S, then we will have more ones than minus ones. So when we sum up all the numbers in the set T, it will be a positive value. So that's how we can transform an input instance of problem A to an input instance of problem B. Now, is this transformation polynomial? Yes, we just need to go through all the elements in the set S once. So it's linear, so it's a polynomial time. Second, is this transformation answer preserving? So we need to prove that when B answers yes, we also have A answers yes. When B answers no, we should also have A answers no. So the first one would be really easy to prove. When B has a positive sum, it means that we have more positive ones than negative ones. So set S will have more positive integers than negative integers. For the second one, instead of proving negative answers, we could prove this instead. If we say, can we have A also answers no when we have B answers no? We can prove this by contradiction. So let's say we assume that when B is no, A is yes. If we know if A is yes, then B is yes. So we'll be able to know then B is yes. And then that is contradictory. So is this true? When A answers yes, do we also have B answers yes? When A answers yes, it means that in set S, there are more positive than negative integers. By looking at the way we converted S to T, that will give us more positive ones than negative ones in the set T. So for sure, B will also answer yes. We can confirm this polynomial time transformation is also answer preserving. Okay, this will be all for this lecture. We are setting the stage for revealing an immensely powerful theorem that revolutionized our understanding of the relationship between easy and hard problems. We will be discussing it in the next two lectures. Stay tuned.